Hello everyone, let's look into the integer numbers or the 64-bit. How do you represent the 64-bit unsigned and signed integer numbers? So that part that we're trying to address over here is, for example, this was the assembler, and these instructions are getting converted into bit patterns like 10, which is being easily understood by the RISC-V implementation or by the chip which implements the RISC-V architecture. Now if we pass some numbers along with these particular instructions, those numbers as well should be understood very well by the implementation, and that's why we need to understand the conversion. First of all, we need to understand what kind of conversion happens once we convert any number from its decimal format, which is a human readable format, to a binary format, and how does things are getting arranged and represented by a RISC-V implementation. So as a result of that, the understanding of integers, understanding of signed and unsigned integers, and the representation in the binary pattern is really very important. So let's start. So basically, if we go back to the basics, the humans understand decimal format and the computers understand binary. So there has to be an interface that converts from something from decimal to binary. So that's why we are trying to address this particular part of the RISC-V implementation. So for example, if this is a decimal number which is in a human readable format, this is its equivalent 64-bit binary number. Okay, we'll get into the signed, unsigned, and all those concepts as and when we go through. The reason we are trying to cover this one is to show you how does the data is getting arranged inside the memory, and how does the instructions gets arranged inside the memory, and so on. All this thing will be very evident as and when we go through the entire flow of the course. So first of all, let's start with the very basics so that we are all on the same page. So this big number which is being seen over here, it's in the decimal format, and its equivalent binary representation in a 64-bit binary representation format, it looks something like this. If you try to break this into two different parts, this is the first 32-bit and this is the highest 32-bit, and let's try to arrange it in a different fashion. So the lowest 32-bit are arranged over here, the highest 32-bit are arranged at this point of time, and each bit has got its associated bit number. So 0 is this particular bit number, 1 is this particular bit number, 46 is this particular bit number, and so on. So there are some new terms that we want to introduce over here, which are very important with respect to any instruction, any RISC-V instruction. So that's why we are trying to cover these concepts right at the beginning of the course. So the entire 64-bit number is being called as the double word in the terms of the RISC-V. In a processor language, it's called as the double word. Okay, any 32-bit integer is called as the word. This is one word, this is the second word, and two words form a double word. So this is called the word, and this is basically called as the least significant bit, which is LSB. This is called as the most significant bit, which is MSB. Okay, and a group of 8 bits, you can use a short form of LSB and MSB directly over here, and moving forward we'll be using MSB and LSB whenever it is needed. If you try to group everything in the form of 8 bits, the 8 bits, a group of 8 bits is called as a byte. So there are like 4 bytes present over here and 4 bytes present over here. So total 4 bytes form a word, and total if you use 8 bytes, that forms a double word. So there are a couple of new terms that we introduce over here. So let's try to brush up everything in a single line, which says that 8 bits form a byte. Okay, which is 8 bits over here, that forms a single byte. 4 bytes form a word. So a word comprises of 4 bytes. 2 words or the 8 bytes. So basically these 2 words form a double word, and these 2 words are nothing but a group of 4 bytes, which makes it 8 bytes. So 8 bytes or 2 words forms a double word, and this line which I have highlighted is really very important, because this decides the way we are going to arrange the patterns inside the RISC-V memory while we are trying to execute any instructions, any RISC-V instructions. Let's say a load double word or a load word instruction. So these kind of instructions needs us the basic understanding of number representation. So this was about the unsigned positive numbers. I'll get back to that in a minute from now. So for example, let's try to see how many patterns can we represent using 64 bits. So let's take a small example. Had this been not a 64, had this been not RISC-V 64, RV64, had this been just RV2 bits. So using 2 bits, we will be able to represent only 4 numbers from 0 to 3. If you try to put it in a formula, it will be 0 to 2 square minus 1, where 2 square, the number 2 which you see over here, that's the number of bits minus 1. So you will be able to represent 0 to 3. Similarly, if there were 3 bits, in the implementation itself, then the number of patterns that will be able to represent was 8, and the number set was 0 to 7, which is nothing but 0 to 2 to the power 3 minus 1. 3 is nothing but again the number of bits which is being used to represent the numbers. And if you had, let's say, 4-bit, so the number of patterns that you will be able to represent was 16. It's 2 to the power 4, which is again the number of bits, and the number counting will be from 0 to 2 to the power 4 minus 1, which is 16 minus 1 and 15. Similarly, using the 64-bit implementation, you will be able to represent 2 to the power 64 numbers. The number of patterns that you will be able to represent will be 2 to the power 64, and the number of patterns or the pattern set will be 0 to 2 to the power 64 minus 1. Okay? This goes along with the existing formula that we have seen for these small cases. So that's one thing. Let's try to identify those numbers. So if you try to expand this 64-bit into its equivalent decimal number, you need to take this particular bit name. You need to take the value of this particular bit, which is logic 1, and multiply it by 2 to the power 0. Since this is a 0th bit, so we have to multiply it by 2 to the power 0. Since this is the first bit, and the value of this particular first bit is 1, so 1 into 2 to the power 1 will give you the value of this one, and you have to keep on adding them. Now, let's say this was the 31st bit, but the value of the 31st bit was 0. So 0 into 2 to the power 31 will give you this one, and you have to keep on doing it for all the bits till you go from 0 to 63rd bit. So in this case, this is the 63rd bit, so you have to 1 into 2 to the power 63, and there is some value that you will be getting over here, and you have to add all of them to get its equivalent decimal number. That's the very simple way to convert any 64-bit or any bit number into its equivalent decimal number. That's one of the basic concepts that we need to be on the same page, because on the basis of this concept we are going to understand some other integers as well. So now since that we know what is the formula to obtain or to convert from 64-bit to a decimal number, let's try to identify the range of numbers that can be represented using RV64. So if this was one of the binary pattern, the lowest number that can be represented by this particular RV64 system will be all zeros. It will be all zeros, and the highest number that can be represented by this particular system will be all ones. Will be all 1. So if you try to expand this one, you just need to multiply 1 into 2 to the power 0 plus 1 into 2 to the power 1 and so on. You need to keep on adding it till the 63rd bit, and this is the final number that you will be able to represent in a decimal format in an RV64. So it essentially means to us that in an RV64 system, if you're trying to do an unsigned addition, you'll be able to add it till this particular number. So any two numbers, if they get added, and if it exceeds this number, there will be another flag which will be called as the overflow flag. We'll talk about that particular flag in a minute from now once we reach there. So there will be an overflow flag that will be getting set. But if you try to ignore that, the amount of the final addition number, the final number or the maximum number that can be added is this one. So addition of two numbers can go max up to this particular value, from 0 to this particular value in an RV64 system. So that concludes one more thing over here, that the number of double words that can be represented using an RV64 system, the number of unsigned numbers or the number of positive numbers that can be represented using a RISC-V 64 system will be 0 to 2 to the power 64 minus 1. So that was about the unsigned and the positive numbers. Now the question comes over here. In addition, you might also do a subtraction. You can also do 2 plus of minus 3, or you can also do 2 minus 3. So what in that case, what do we do? So we need to find out a way to represent the signed numbers as well. So basically we need to find out a way to represent the negative numbers as well. So what we'll do is we'll stop at this point and we'll find out a way how do we represent the negative numbers in the next video. Thank you.